Organic chemistry is important because it's the basis of all life, and most of our molecules that are in the world are organic in nature. And so we are talking about this at the end of the year here as a way to prepare you for chemistry if you take the third semester, or for biology if you're taking that next year, which all of you should be. So with that in mind, you are welcome and invited to stop at any point to write anything down. I highly recommend, once we do some of the practice problems, that you pause the video, try it yourself, and then watch me go through it. So what makes carbon so special? Well, one thing, carbon can form multiple bonds, and that means that it can form either single bonds, double bonds, or triple bonds with itself and other atoms. The carbon-carbon bond is strong, so it's thermally stable, and the carbon-hydrogen bond is also strong and stable. Carbon can form chains as well as rings, and carbon is unable to expand its octet, which means that it can form no more than 4 bonds. So it's really predictable, which makes life easier for us. So naming organic molecules is going to be different from the naming that you learned earlier this year with ionic compounds and covalent compounds, even though it has some of those same bonding habits that a covalent or an ionic compound would, but these are much larger most of the time and so require some special naming. So one of the types of organic molecules that we have are called alkanes. And an alkane is where all of the carbon bonds are singly bonded. And we know carbon and hydrogen can only ever be a single bond. And if it's just a straight up alkane, there's no other elements besides carbons or hydrogens in it. And so we get down here a general formula for an alkane. So this is kind of the mathematical way of thinking about it, where N is however many carbons you have. So let's say you have just 1 carbon. That would mean that carbon is 1, and we don't have to write the 1 because we're used to that. And then hydrogen would be 2 times 1 plus 2, which is 4. So CH4 is the first molecule that we can have in organic chemistry. It's the most simple one that there is. And the way that we name them is with an ANE at the end. So suffix is at the end of the name, ane. So CH4 was what we just saw. That's called methane. So we see that ANE from the name of only single bonds, and meth means 1. So kind of like before covalent molecules, so instead of mono, we have meth representing 1. So the molecular formula is what we have right here. And if we remember to the very beginning of chemistry this year, a molecular formula is just the total number of all atoms in a molecule. The condensed structural formula is going to actually show no bonds, whereas the full structural formula, which is the first part that it's asking us here, shows all of the bonds. So we put carbon in the middle because that needs the most bonds. Hydrogen can only have 1 bond, so we have C, H, 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 and H. That's my full structural formula. That's how methane is put together. 1 carbon in the middle, 4 hydrogens around it. And you probably did one of these back when we were doing structural formulas. And so you might remember looking at this and saying, oh, that's a tetrahedral molecule, and in 3 dimensions the angle is 109.5, which is so weird because it looks like they're 90-degree angles, but 3 dimensions makes it different. So that's a little refresher for us. Now the condensed structural formula is going to be something that no bonds are shown, and it's written on a line. So you can anticipate that people that are producing textbooks are much more fond of these condensed structural formulas because they don't have to take up so much space. So the condensed structural formula here is just my carbon with 1, 2, 3, 4 hydrogens around it, CH4, and we see that the condensed structural formula is the same as the molecular formula here. Ethane, ane we said means single bonds, and S stands for 2 carbons. That stands for 2, and we see that right here, C2. So the carbons are going to attach to one another with a single bond, C, C. And to fill up the rest of the bonds, because we know that carbon needs 4 bonds, it's going to have 1, 2, 3, 1, 2, 3. We fill those hydrogens in, H, 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 and H, and we see that there are indeed 1, 2, 3, 4, 5, 6 hydrogens total in that molecule. So there's my full structural formula. Now, if I wanted to draw the condensed structural formula, that's taking the bonds out and writing it on one line. So my carbon here has 3 hydrogens attached. So I would have CH3, and then this carbon is right next to it, so I'm going to have a C there, and it has 1, 2, 3 hydrogens around it as well. So the condensed structural formula would be written as CH3, CH3. Now we can draw C4H10 in 2 different ways, 2 unique ways. So one unique way is always going to be just in one line. 1 carbon, 2 carbons, 3 carbons, 4 carbons. And each of those carbons should have 4 bonds. This one right now only has 1, so it needs 1, 2, 3. This one has 2, so it's going to need 2 more. This one has 2, so it needs 2 more. And this one needs 3 more, because it only has 1 to start with. And I know for a fact, based off of the formula, that these are just hydrogens. We haven't done anything yet with oxygens, nitrogens, or anything else. Okay, so this is the easiest structural isomer for C4H10. But I can draw this another way, with it all still being singly bonded carbons and singly bonded hydrogens for a total of C4H10. So what we can do is imagine that I am going to rip off this end here. And I'm going to rip off this hydrogen here. And I'm going to switch their places. So now I have 1, 2, 3 carbons in a row with 1 carbon coming off of this center carbon. And then I need to check my hydrogens. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's write them all in. So now this molecule is completely different from this one, even though they have the same formula. Okay, they have the same molecular formula, but they're 2 different molecules, and they actually do behave differently with their physical as well as chemical properties, and that is why structural isomers matter. It's because they're going to react differently and they're going to behave differently, even though they have the same molecular formula. Now, if we think back early to this year, we also discussed empirical formula. This is the lowest ratio from the molecular formula. Can we divide by something? Do any numbers go into both 4 and 10? Hopefully you're saying, oh yeah, we can divide that by 2. And the empirical formula then would be C2H5. Now the condensed structural formula for each of these is going to be different because they're both put together in different ways. So this one, CH3, CH2, CH2, CH3. Now here's a trick because chemists like to be lazy whenever possible. When you have something that is repeating and not on the end, so in the middle of a long line that's repeating, we can say, well, here's one end, here's my other end, but these repeat, so I'm going to have CH2 two times. So that's my way to make the condensed structural formula smaller. And both of these are okay, but again, chemists sometimes just like being lazy. In the best ways possible, of course. This one is going to be different because it starts with that CH3, then it has a CH, and off the top of that CH we have the CH3 right there. So we put that in parentheses to help us know that this is coming off of that. So when we see a parentheses like that, we know, well, carbon has to have 4 bonds. Here's 1 bond, here's 2 bonds. Here's the CH3 at the end. That means that this CH3 is coming off the middle. And as we see, since we need to keep the ends the same, nothing in the middle of this one repeats, so there's no other way to make it a further condensed structural formula. We're going to come back to these two later because they're named in a different way from one another. And we'll see how that is. So, IUPAC, rules for naming chains of molecules. So our previous naming rules for covalent and ionic molecules, they were IUPAC as well. These are different though because we've got an organic molecule which tends to be quite big. So first thing that we have to do is name the longest continuous carbon chain. Then we identify any groups that are attached, which we haven't talked about any of those yet, so that'll come a little bit later. Then we number the chain consecutively, starting at the end nearest a substituent group, and a substituent group are just those things off of the main chain. And then we assemble the name, listing the groups in alphabetical order. Here's some prefixes. We've seen a couple of them already. We saw meth representing 1, F representing 2. We skipped this one for now, but here we see 3 is prop. 4 is bute, we saw that one in the previous problem. 5 is pent, and 6 is hex. Now sometimes, as we saw 2 slides ago, we have a CH3 group that's attached to the main chain. And when we see that, it's called an alkyl group, and it's represented with a functional group. So if we go back here, we say the substituent group, it's something off the main chain, we name it differently. So we would have a methyl on it. So let's say I've got a chain, I started to do it semi-condensed there, sorry. Okay, so if I look at that problem from before where I had that I have a methyl group off of my main chain. So let's look at what that does for us here. So if we look at that unique structural isomer of C4H10, we had 2 different ones. They had the same molecular formula and the same empirical formula, but their structure, their full structural formula, their name, and their condensed structural formula, which I have down here already, those are going to be different. So we saw a few slides back that we need to first find and name the longest continuous carbon chain. So here I've got 1, 2, 3, 4 carbons all in a row. And on this one I just have 1, 2, 3 carbons in a row. That's my longest. So I can go back here and say once I've done that, that tells me the prefix that I have from here. And then I can identify any groups that are attached. So in this one, I have something that's not a hydrogen in the place where a hydrogen would have been, and this is a methyl group. So I have a methyl group on my chain of 3, and if I look back here, 3 is prop. I also have a chain of 4 that's bute. So I can go back here, 1, 2, 3, 4, with nothing else on that. This one's easy, it's just called butane. This one has a prop They're all singly bonded, so we know it's an ane. And I have the special methyl group off of it. So I start in alphabetical order with the functional groups that are attached to it with this methyl, and then propane. Now, most of the time, when we have something coming off the main chain, we're going to have to identify which carbon it's on. But in this instance, the only place that I could have that methyl group is on that middle carbon. Because if I move it to either of the ends, so let's say I switch out that hydrogen with that methyl group, that would just be the same thing as 1, 2, 3, 4 in a row. It'd still be butane. So even if I drew it funny with the CH3 up here, it would be the same thing. So either I could have butane or methylpropane, and both of them had this structural formula, or the molecular formula of C4H10. Okay, let's look at C5H12. So 5, if we look back a few slides, that's a pent. And it follows that formula of CnH2n plus 2, so we know that it's an alkane. So it's going to end with a suffix of ane. And I'm going to start out by doing the easy one, so 5 in a row. 3, 4, 5, and I know that each carbon has to have 4 bonds, so this one has 3 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, and here we go, 3 hydrogens on the end. If I were to do the condensed structural formula, it'd be CH3, CH2 3 times, and CH3. So here's the full structural formula, here's the condensed structural formula, and if I were to name it, I would count the longest chain, 1, 2, 3, 4, 5, so I know 5 is pent, and I see that they're all singly bonded, so I know it's going to end with an ane, and there's nothing around the carbons except for hydrogens, so it's our simple one to name, pentane. Okay, now my next one, let's imagine, just like we did with the last one, let us take off the CH3 that's on the end and replace one of the hydrogens that's on a different part of the chain. So we have 1, 2, 3, 4 with a CH3 group. We'll get the rest of these in as well. Okay, now each carbon has 4 bonds, each hydrogen only has 1. If I were to do the condensed structural formula, I could start writing it from either side. CH3, CH2, CH, CH3 coming off of that CH2, and a CH3. And if I'm naming it, I have here a group coming off. That's a methyl. And I see that this methyl group is closer to this end, and so I'm going to start counting from the end nearest to a substituent group. That was one of our rules from before for naming. Okay, we assemble, or look, name it, number it, consecutively starting at the end nearest a substituent group. So someplace where I've substituted a hydrogen for something else. So my methyl group is going to be part of it, and I'm going to start counting over here. 1, 2, 3, 4. 4 has a prefix of but, and then we know that they're all singly bonded, so we know it's a butane as the end part of the name. Butane, and I have a methyl coming off of the second one. 2-methyl butane. But let's just think for a second. Let's imagine that instead of this hydrogen, I had switched it out with this one instead. So if I were to draw that out, I'd have 1, 2, 3, 4. I'd have my CH3 here, and it looks different, right? If I was trying to put this on top of that one, it looks different. But if we follow those rules again, I would need to start counting from this side because this end carbon is closer to where I've moved the substituent group. So we have 1, 2, 3, 4 this time, and we've got on the second carbon a methyl group. So even if I drew it a different way, I would still have 2-methyl butane, same molecule. So that doesn't give me something new. There is one more unique structure though that's not listed here. And what I would do is take off another CH3 and switch it with one of the hydrogens in the middle. So this time we're going to switch these out. And so this is another molecule, a unique structural isomer. So it's structured in a different way than the other two, but it still has this general formula of C5H12. And so we name it differently and we write the condensed structural formula differently. We would say we have a CH3 and then a C with 2 CH3s off of it, and then a CH3 at the end. Again, we always leave those as they are, and then the middles is where we can condense stuff if we need to. And so in this one, I have a methyl group here, but I also have a methyl group here. And there's no carbons that they can be on besides that middle one, so technically we wouldn't need to write the numbers on this one. But we see 1, 2, 3, that means I've got a prop. We see they're all singly bonded, which means I have an ane. So the end of my name is propane. And then I've got 2 methyl groups. So if we see this note down here, when I have multiples of the same group, if I have 2 of them, I could call them di. So I've got dimethyl propane. I have 2 methyl groups off of my propane chain. Alkene, so we go from alkane to alkene, and alkene has a double bond. And it's got this general formula. If you notice, the only thing that it's missing from an alkane is 2 hydrogens, because it's normally a +2 here. So we know that that's going to be different. And now we have an ene, and we have to identify what numbered carbon that ene is on. So this is like with that substituent group. So the first alkene, C2H4, the carbons are in the center as a double bond, and I know it's going to be a double bond because of an ene. And then we have a hydrogen, 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 hydrogen. Each carbon has 4 bonds. Each hydrogen has 1, so that's a good molecule there. The condensed structural formula is CH2, CH2, because again, we keep whatever our ends are the same. If there was stuff in the middle, we could potentially condense them more. And there are 2 carbons, so 2 is F, and then they're doubly bonded here, so that's ene. C4H8. What are 2 different ways to draw out C4H8 in a straight chain? So I'm going to do a little note here. This is just in a straight chain. There's going to be other things that you could do as well, but we're just going to look at the most basic. 2, 3, 4. So I could have that double bond in between the first and the second carbon. My other one would put my double bond between my second and third. Then structural formulas, we would just say CH2CH, CH2CH3, or CH3CH. We can say that goes twice in a CH3. And the names are different because of where this double bond is. So we know it's going to be an ene. If there's any double bonds, it's going to be an ene. And then we know that there's going to be 1, 2, 3, 4 in each of them, and we know that 4 is but as the prefix. And we see that on this one, the ene starts on the first carbon. So we have but 1, because it starts on the first carbon, ene. And on this one, it starts on the second carbon, so it's but2-ene. Or if you don't like it with the number in between telling us where the double bond starts, you could start out your compound with a 1, butene, or 2, butene. This one be named, what's the molecular formula and what's the empirical formula? So 1, 2, 3, 4, 5, C5, molecular formula, total number of each element. So I just counted 5 carbons. My hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5H10. Empirical formula is that, can I reduce this at all? And sure enough, I can divide both by the 5, C1, 5 divided by 5 is 1, H2, 10 divided by 5 is 2. So that's how I get that empirical formula there. But there's 4 in the total, so that's a but. And we know that there's a double bond, so that's an ene. And we know that the double bond starts on the first carbon. So we would have a 1 butene with a 2-methyl group. So 2-methyl, 1-butene. Or if we like that one in between, so we remember that that's what that is referring to, we could call it 2-methyl, 1-but, 1-ene. Either of those work. I have a triple bond, so 6 electrons shared between a carbon. And the general formula now has changed, CnH2n minus 2. So I've gotten rid of 2 more hydrogens in order to form that triple bond. And so I have that number again that identifies which carbon the triple bond starts on, and then an yne at the end, Y-N-E. So the first alkyne, so we would draw it C, triple bond, C, H, H. Each hydrogen has 1 bond, each carbon has 4, so that's the full structural formula. The condensed structural formula would be CH, CH, because we write out both of the ends. If there had been stuff in the middle, then we could have condensed it, but we can't because those are the ends. And there are 2 carbons. 2 carbons is an F, and a triple bond is a Y-N-E. There's only one place for it to start. It's starting on the first carbon, so I don't need to do the number for this one. Oops. So we would call it ethane. That's my structure. My condensed would be CH, C, CH3. I could rewrite this the other way and it would be the same thing. We only have one name for this. There's 1, 2, 3 places. There's only one way that I can draw it, so that means that the triple bond is always starting on the first carbon. Triple bond means it's an yne. 3 means it's a prop. So propyne. There's 2 different ways that we can draw C4H6. So we start out here, 2, 3, 4. I'm going to put my triple bond first on that first carbon. And so this carbon needs 1 more hydrogen. That carbon already has 4 bonds. This carbon needs 2 more. And this carbon needs 3 more. So there's one structure. My second structure would be to move that triple bond over to the next carbon. So I would have C, C, triple bond, C, C. And I've got 3 hydrogens here. This carbon already has 4, and this carbon already has 4, so my last 3 hydrogens go on the end. Notice that this can't be flipped with this one like the last one could be, so these are 2 totally different structures. On this one, my triple bond is starting on the first carbon, so it's 1 yne, and there's 1, 2, 3, 4 carbons total, so it's a but. And then over here, my triple bond is starting on the second carbon, so it's a 2 yne. Okay, And that again is a bute because there's 4 of them. So here we have either 1 butine, or we could rewrite this as bute 1 ine, and then 2 butine, or we could write it bute 2 ine. And really it's just a matter of preference. Those mean the same thing and those mean the same thing. So it's really a matter of preference. If we want to do the condensed structural formula, we just take out all the bonds, CH, C, CH2, CH3, and then my second one is CH3, C2, CH3. Okay, naming this one. We know that the triple bond is going to be part of the main chain, even though I've got this really weird, like 90-degree angle that we're not used to. But it is actually an important bond for us here. So here's my first carbon, here's my second carbon, third carbon, fourth carbon, and either one of these could be the end of my chain. I'm just going to call this one my fifth. So here's a pent, here's an ine on the first carbon, and here I have a methyl group on the fourth carbon. So the molecular formula is just counting out all of the total number of carbons and hydrogens. I've got 1, 2, 3, 4, 5, 6 carbons, C6, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which makes sense because that's CN H2N minus 2, so mathematically that works, thank goodness. And then the empirical formula, I just ask myself, can this be divided by anything in whole numbers? And sure enough, 2 goes into both of them, so C3H5. Now back to naming it. So let's put all of these parts together. This methyl is going to be listed first, so 4-methyl. And then we have the pent, and we could start out with where the ine is, 1-pentyne, or we could name this 4-methyl pent 1-ine. Either way works. There are a whole bunch of other types of functional groups, and some of the key ones to both biology as well as further chemistry are going to be listed on the next slides. First, we have an alcohol group, which we call the group a hydroxyl because it's an OH. We've seen that before, right? Quite a bit. So an OH is a hydroxyl. We would replace the A and E of a name like methane, propane, butane with anol. And that tells us that we have an alcohol, OL, in that spot. And we have to indicate the number. So let's put the number sign here, the number that it is on. So methanol and ethanol both only have one unique way to write the full structural formula. So there's only one way to name them. Meth means 1. Eth means 2. So this one's just going to have 1. And what I do is I replace one of the hydrogens that I normally have with an OH. And you don't need to show the bond in between the O and the H. It's one of those spots where chemists get a little bit lazy in a good way. Ethane means 2 carbons. And again, I just replace one of the spots where there would normally be a hydrogen with an OH. Okay, condensed structural formula, CH3OH, CH3, CH2, OH. Notice that I don't lump this hydrogen in with those, or that one with those, because we want to make sure that we know that it's an alcohol hydroxyl group and not that it's something else. Propanol has 2 unique structures, so prop meaning 3 carbons, all meaning the fact that it has an OH. So two totally different ways to write them, so two totally different ways to name them. 1, 2, 3, 1, 2, 3. I'm going to put my OH here right away on this first carbon. And I know it's my first carbon because it's the closest to where I have a substituent group. So something substituting the spot that I have a hydrogen. So this is my first one. So the name of this one is 1-propanol or propan 1-all, either way. And then my next one, I have to put on this second carbon. So I replace one of the hydrogens with an OH. And then I fill in the rest of my hydrogens. And I get 2-propanol or propan 2-all. Now you might be asking, well, isn't there a third? Can't we do 1, 2, 3 with the OH on this last carbon? But that gets us back to our naming rules, which say that we start counting from wherever our substituent group. So if our substituent group is here, we start counting here. 1, 2, 3. So it's still on that first carbon just like it was here. So even though I've written it differently, these are the same. Now we could have also put this OH here instead or here instead. Either way, it's on the first carbon, and that's what matters. It doesn't matter where I drew it, if I drew it up or down or on the side. It doesn't matter. It's all on that first carbon. Butanol also has two unique structures, so but meaning 4, and all meaning that I've got an OH group on it. Has two unique structures. And notice, like, this doesn't say diol or triol or anything like that, which means that there's just one OH. Remember, we looked at those dis and tris before, meaning that there could be more of them. But there's only two ways to draw this. 3, 4. 1, 2, 3, 4. We can either be on this first carbon or the second carbon. And same rules apply that we had last time. We could move these around to these last two carbons to the right, and it would still either be on the first carbon or the second carbon, just because we have to count from the other direction. So this is on my first one, so 1-butanol or on 2-butanol. And now we want to know how this one is named. I've got a lot going on here, right? So my main chain, 1, 2, 3, 4, 5, 6 carbons in a row. Right here, I have 2 carbons that are coming off, so it's an ethyl group on the third carbon, so 3-ethyl. Here I have a methyl group on the fourth carbon, so 4-methyl, and I've got an OH here and an OH here, so I have 2,4-diol. Okay, and 6 total means hex. So alphabetical order, the ethyl is going to come before the methyl. So we have 3-ethyl, 4-methyl,